This test demonstrates the two-engine inoperative condition, one of the most critical safety requirements for our design. The live trajectory graph shown alongside the video confirms that even with two engines disabled, the prototype maintains stable control in all three axes. This validates our prediction that the hexacopter configuration provides sufficient redundancy for safe, controlled flight at full scale, even under severe propulsion failures. Here, the 20% scale validation model is flown through unscripted maneuvers to stress test the configuration. The purpose of this early test was to confirm our prediction that the novel hexacopter layout would remain controllable and stable before committing to the larger 35% prototype. The results directly reduced the risk of uncontrolled flight in later tests, validating both our aerodynamic predictions and the control strategy to be used in the full-scale system. The prototype arm was statically tested by suspending a 10 kg mass at its tip, representing a worst-case bending load. The arm did not fail or show excessive deflection, confirming the Euler-Bernoulli analytical prediction. Furthermore, both the 35% and 20% scale vehicles completed flight testing without observable structural degradation, providing additional confidence in the adequacy of the design. Since the analytical method, supported by static load testing and dynamic flight testing, correctly predicted safe performance at reduced scale, it can be concluded with confidence that the same Euler-Bernoulli beam theory approach ensures the full 100% scale vehicle will also satisfy structural requirements. In parallel with flight testing, we are developing autonomy features within the gazebo simulation environment. This platform allows us to safely test mission planning, obstacle avoidance, and control logic before deploying them to the physical prototype. By validating autonomy in simulation first, we reduce risk and accelerate integration of these capabilities into the full-scale system. To validate our propulsion model, we compared thrust predictions from blade element momentum theory against experimental data using the 35% prototype's motor and propeller. The results show a strong correlation, with only minor overprediction due to unmodeled system losses. After applying an efficiency factor, the model closely matches reality. This confirms that our propulsion code reliably predicts thrust and power requirements, giving confidence that the full-scale vehicle will meet its performance targets. Together, these results provide strong evidence that the full-scale vehicle will meet its predicted performance with confidence and reliability.